Good morning. So welcome to this first session on the first University Day at DevOps. Oh my God, I'm really standing here. Can't believe it. I submitted a talk with such a title that you would believe it would never go through. It's like totally buzzword compliant and even includes the word buzzwords. I'm very proud of that. And it actually got accepted. Who would have thought? So what's behind this mouthful? I actually want to discuss a couple of things. First off, I want to start by stepping back, looking at the way we've been doing accessing data for quite a while now. And then I'll talk about all the cool buzzwords, so big data, NoSQL, distributed systems. I want to look also a little bit into, throughout the presentation, at the nature of data, and we'll see that not all data is born equal. I think that's an important fact. And then we'll look into applications of all this. So we'll look into queues, caches, CQRS, thing, other buzzword, and other stuff. So quickly about me. So I've been working at Terracotta for almost 5 years now. And Terracotta handled large amounts of data for quite a while, and a bunch of different data that is used for many different things. One non-neglectable being all the sensors, the 130,000 sensors on the LHC at CERN in Switzerland are being all handled through Terracotta. So if by the end of this presentation the world collapses into a black hole, it might be my fault. Nobody will be there to blame me for that. And so Terracotta used to be a startup, and we got acquired, so there would be no real presentation without the disclaimer slide. I made it as small as possible. I knew there would be a big screen, so that kind of works. So it's all nonsense, as you can see. Except maybe the first bullet point, and that probably should apply to about any conference you go to. And the please don't sue me also applies. So whatever I say, please don't sue me. All right, so let's go into it. So once upon a time, we developers writing code, mainly object-oriented code. So we write classes that we instantiate, and all that goes into memory. And we have all our state in memory. That's awesome. Though apparently sometimes we need to restart applications, sometimes we need to upgrade applications, which involves a restart, and things like that. So we need to have all the state that we have in memory be persisted somewhere. So on computers, we generally persist stuff on this thing called disk, and one's called platters that rotate it. And so where does all that data live? Whatever the data that represents the state of our objects goes into a relational database. That's the way that we've been persisting data, and certainly in the enterprise world, but actually beyond that, right? So go install any blogging software today for your own personal site, well, will be the data persisted inside a relational database. So relational databases look at the world like this. Wow, that's really fuzzy. That's a drug database. There was actually a joke there, but nobody can see it. Don't draw any conclusion from that, though. So we have tables that have columns that are very known types, and all those things relate to each other. So I can apply constraints, and that's the way that we persist the state of our objects on disk. So this leads to a well-known problem called the impedance mismatch, because actually the two paradigms don't actually really fit each other. But that's fine, because in the meantime, we're all using our ORMs. So who's persisting state in a relational database? Quickly here. Let's do it the other way around. Who is persisting state but not in a relational database? We have a couple of people wonder whether persisted. There is nothing else than a relational database. So, and for the people who are using a relational database, who's using an ORM? And who is not? All right. 2. All right, you should get together after the conference, apparently. So we use ORMs, and ORMs let us think about our data in a much simplified way. Actually, the way that we think about it when we think in terms of object, right? So if I take this stupid example of an invoice is composed of invoice lines, right? Probably also an address or other stuff, but that's just a simple example, right? But as you can see from this simple diagram, an invoice line by itself has no semantic, right? It only exists within an invoice. And so those things are what we call aggregates, right? So it's a bunch of things that we think of as that of one. And so since we're in a relational database, an invoice has a unique ID, and that's what I need to know. I don't care about the invoice line. Once I've set up my ORM, my 20,000 XML files and stuff, I can get to the data sort of transparently. Though sometimes it's actually useful to look at the data slightly differently. So say we're a service company and we invoice services. And we want to know what services bring the most money. All of a sudden, I can look at the composition in a different way, right? I can think of my services that relates to invoice lines, right? Because it's a relational database, so inside every invoice line, I got a reference, a foreign key to the service that was invoiced there. And I can then produce awesome reports that tell me, like, per service type, what is the revenue that it generated for a given period, right? And that's stuff that, if you look at this model here, actually wouldn't really work. I guess if you would model this in OO, you wouldn't really have this relationship from the where you take a service and then you can look at all the invoice lines, right? But using SQL, we can easily create such a report and a couple of SQL statements. So that's nice. And the nice stuff that RDBMS has brought us is, who knows this book? Right. So this book, it talks about how to integrate stuff. And in enterprise, we managed to address a particular problem using RDBMSes. So how can I integrate multiple applications so that they work together and can share information? Well, I can use my beloved database for that, right? I integrate applications by having them store their data in a single shared database. So that's exactly how it's stated in the book and on the website and stuff. So I got a single database access from multiple applications, and now they all share state. Who's seen this in his career? Right. I actually challenged that the others are lying to me, or I really need to take their company name down because they all only work with awesome enterprises. Sometimes, though, they don't necessarily all write to the database, but the most common example is the one that I took, which is the reporting, right? You just access a view inside a production database of application foo, and you look into that and draw conclusions from that. So, summary, so we got our RDBMSes, which are relational. They got a fixed schema, right? A fixed finite set of tables, finite set of columns inside those tables. All those columns have well-defined types. I can express further constraints that I know the database will enforce for me, right? So a field that can never be null, a column that can never be null, a column that references another primary key in another table. They also provide me with something really, really nice, and that's ACID transactions, which are also that we can also roll back. That's a very powerful statement, well, a very powerful thing, right? So now we can do stuff. If an exception happens, something like we didn't plan, we just, like, all frameworks do that for us anyways. We just roll back the transaction. Everything I made in the database gets rolled back. Nobody has seen anything. Awesome. Moving on. And as I said, you can look at the data from about any angle, right? And so those ACID transactions, atomic, right? Either everything happens or nothing happens. They're consistent, so I don't start sharing state across multiple transactions. Whatever the constraints are on that I set on the database will be obeyed. They're isolated. That's really awesome, right? That's probably one of the best points of ACID transaction. It's like you're the only guy in the world. You can do anything you want, and nobody starts interacting weirdly with you in the general case. And they're durable. And that's actually the initial problem we had, right? So we want to store stuff, so we want to have our state being durable. Funnily enough, that's the last point in an ACID thing. Those transactions, though, on the other end, they're very pessimistic. So they're implemented using locking. So when a change is to a field, I shouldn't use that word. When a change is pending to a value inside a row, and within a transaction, and another transaction comes around, it needs to make a decision depending on the isolation level on what should happen, right? Most of the time, you will not be able to access the data until the other transaction that's mutating the data commits, and then you move forward. Transaction also have this, well, transaction or RDBMS generally have this processor affinity. When I say processor in this case, I don't really mean like CPU or dice or whatever. I mean this like basically this machine, more fundamentally. One very obvious example why this is an issue, or at least what's complicated to not have that, is joins, right? As soon as you start joining data, if you need to join two separate set of data that lives on different machine, well, obviously one machine needs to know about the other set, which implies moving the data. And moving data is a really costly operation. It's the thing you actually try to avoid do the most in distributed system. So it's very costly, and this particular data set could be really large. But using those databases, we've been developing enterprise solutions using generally this 3-tier model, some UI layer, I don't know, Tomcat serving HTML stuff. I got a middle tier that does things, and I got a database, right? So my UI displays action. My middle tier certainly does ORM stuff in order to read data. And there is a bunch, read or mutate data, and there's a bunch of services we get from the database, right? Search, transactions, caching, right? Because once the database has read a bunch of stuff off disk, it will keep it around. So it has a bunch of optimization, right? Those databases have been around for a little while, so they had time to think about the problem set. Batches operation, everything, I get all that in my, handle at the database level. I don't really have to handle all that stuff in the middle tier. So that's really, really nice. And as I said, we've been doing this for a long time. Database, RDBMS has been around for over 30 years now. And that's the one toolkit we've been using to solve many, many problems. Again, particularly enterprise problems, even though I must say I'm very, very still amazed that if I want to roll my own blog for like my 20 blocks article every 10 years, I need to have RDBMS installed somewhere. And then big data happened. Ding. Buzzword. So what's big data? First thing that brings to my mind every time I hear about big data is this statement made by someone, supposedly Bill Gates, though apparently it's not true. But most probably somebody said that at some point. And basically what I want to highlight with this is that there always is a situation where you need to handle stuff that won't fit on wherever you are, right? So think of that back in the days. You had 640K of RAM, and that's what you had, right? The operating system would actually like impose that on you, so whatever you had, that's what you could use. So now all of a sudden, if you have any data set that's larger than this, what do I do, right? And I need to look at this data set at once. So actually, that's to me a pretty good definition of big data, right? It's a data set that I can't handle given my current constraints, right? Whatever these are. Nowadays, any application server has tens of gigs of RAM, but there are data sets bigger than that today. And data sets that are big today are the ones that are going to be small tomorrow, right? That's pretty awesome. So I searched for that a little bit on the internet. That's a hard drive, 10 megabytes for 3.5 grand. Isn't that a deal? Pretty awesome. It's big, obviously, because it's big data. And so this definition of big really changes. I remember buying this hard drive. I actually think I lie. I don't think that's the first 10 gig hard drive that I bought. And I bought this hard drive and I was like, crap, what am I going to do with that, right? 10 gigabyte. That was probably late 90s. And I'm like, how am I ever going to fill this? This is so not going to happen. I mean, what do you do on a computer? Back then I was doing some C stuff. 10 gigabytes of C code, that would be about hell. So what would you ever do with this, right? Well, the one thing that I didn't realize is that computers just become the thing. They handle about everything, right? So this computer, finally, Apple released software out of the hardware out of the factory with a bigger than 256 gigabyte of SSD. I was so happy because 256 was actually too big, too small. Like I was always on the edge. I have to move stuff because now in the meantime, what do you have on your hard drive? About everything. You have books, you have movies, TV shows that you download online. You have pictures. I have some code, not too much. Word documents, Excel sheets, right? You got a bunch of different sets of data, and all that ends up somewhere on the hard drive somewhere. Hopefully not on a platter anymore, but sometimes still on a platter that rotates. And I think those three things give for a fairly good definition of big data. I.e., yes, volume, the very obvious one. Yes, it's just too much data. Well, another one that I don't really cover in those three sort of analogies is the velocity, the speed at which data comes around. And then there are obviously two ways of looking at it. Either you need to read that data really fast, it's being pushed to you, and you need to digest that like really, really quickly. So you need to be fast because, again, right? Think about the 64K analogy, right? If you can't handle the data big enough, like because everything in computer, whenever there is a problem, and you'll see I have slides that proves that, you just put a queue. That's the way that we solve all problems in the computer industry. So you put a queue, but this queue will just grow, and at some point there will not be enough room anymore, and you're dead. So that's the read. The write is exactly the same problem. If I'm under I'll have an example later. Say I've got a website that on every request needs to do a write. Most probably at some point I'm going to have a problem, right? If I'm successful with my website, it's just not going to work. And last but not least, like unstructured data. I have data that comes from, I can get data that comes from about anywhere, right? Twitter streams, social stuff, again, all my movie collections, my code, whatever. There is data in about any form, and form that morphs all the time, right? So the way that today, I think I use that as an example later, but so who knows about Jenkins, the the continuous integration server? So Jenkins is something really cool that's all like very API driven, and you can just hit about any URL, just add API/something, XML, JSON, whatever, and you can look at the raw data that this thing produces. Though with depending on the plugins installed, like it will give you a different set of data because say I don't know, you get the very simply like the JUnit report plugin, right? And you run tests that will be part of your result set. Now somebody installs some fancy plugin that like adds information to this, and you have more information that you didn't know about, but all of a sudden it appeared, right? And there is actually another point to big data, I think, at least to the way that we should think about it. And that's Agile Data. Ding, buzzword, I got Agile in there, that's probably good. And the point is to be data-driven. So if I retake this example from Jenkins, right, and I actually took a crack at looking at, so Terracotta, since we're running on very multiple like operating systems, some includes one called AIX, for instance. We run on very different VMs, some of them running on AIX, for instance, coming from a certain vendor. We need to test our stuff on everything. So we got a pretty large, what we call a monkey farm, that run all our tests on all variations of platforms, permutation of JDKs, memory models, blah, blah, blah. And I thought I wanted to have a look at this data differently. So I imported all this JSON stuff. If I would have had to go through all the JSON documents, all the possible answers that even Jenkins gives me, right? Because I said, like, depending on the set of plugins that are installed, you could get a different result. But also on the kind of build that was actually built, you will get a very different result. I think Jenkins comes, I think it's out of the box with like a Maven build that builds a Maven build, and another one that's so-called a freestyle build that builds about it. It could be building about anything. Well, the two results look different. I didn't know about that. And if I would have had to spend all my time looking at all this data inside and like edit XML files or annotate classes in order to populate a domain model to be able to look at this data, and actually, as I do all this, only start understanding it, this would have taken days, right? So with certain data store, as we'll see later, you can just not care about all this. You can, me as a developer that tries to understand the problem set, I can just go get all that data, feed it somewhere, and then start querying it, right? So, again, taking the Jenkins example, we got stuff running all the time. It's a continuous flow of information that comes to my system. We got our infrastructure guy that actually, well, guys, that actually do stuff, change things. We got developers that actually also do stuff, change other stuff, and all that creates this fuzzy data representation of a problem that I'm not even sure I understand, but I want to look at. And so instead of spending all my time around mapping files and so forth, I can just feed all the data in and then start querying it to actually start making sense of it, right? Play with the data, really raw. Took me probably, well, since I wrote that in Java, and I think there is a Scala thing afterwards, so it's very verbose, so I think it took me probably 30 lines of code or something to go fetch the data and start inserting it inside, in that case, a document store. And I think that's very powerful. Talking about document store, so this is all about the NoSQL. That's also very, again, buzzword, cool. So NoSQL, very, very weird concept, something that defines itself by what it's not. Hi, I'm Alex, I'm not a project manager. Just in case you wondered, I'm not. Helps you a lot to know who I am now. So what's up with all that? Well, given what, like, bunch of things to which I hinted already, what was the drive behind all those NoSQL store, right? So I guess, looking at them, that's my take on this. I might be missing stuff. If somebody wants to add something, feel free to interject. They're certainly distributed in nature. All those systems have the size, it's not if you'll be distributed. There is not a single node doing something. It's a bunch of nodes doing stuff, right? When you think about all the big table and other paper that came out, it's just people that scaled out, not up. They don't buy those huge Oracle rack thing, looking really fancy. No, they build their own hardware, commodity hardware, roll it inside huge data centers, and they just run the huge data sets on that. As it turns out, none of them is applying any set theory as RDBMSes do. There is no relationships and there is no joins. Well, sorry, that wasn't the right word. There are no relations in the set theory sense, and there are no joins. They're schemaless. I don't necessarily have to be very verbose about the kind of data that I will use. Again, there are exceptions to everything I say, but generally they're schemaless. You can enforce schema on some of them so that you validate documents that come in instead of just storing about anything. But fundamentally schemaless. They're low latency, and I'll come back to that in a sec. I realize actually there is one bullet point that I missed there. Well, actually no. They're distributed in nature. So when you have a cluster of hundreds of machines, it's not a matter if one fails, it's a matter when one fails. And the more machines you have, the sooner it'll fail. That's just a fact of distributed systems. That's what's cool about having everything on a single machine, right? When it fails, obviously the service is down, the machine's dead. So low latency. That's something I stole from Jens Bonner on his GitHub account. There are all the sources where he found all that data. And so these are the latency numbers every programmer should know. So if you hadn't seen this yet, I think this is interesting. In the particular subject matter here, though, we care about a much smaller data set, which is this one. And I think looking at those numbers in perspective is interesting, right? So sending 1K over a 1 gigabit network takes 0.01 milliseconds, which if we do the math to make it to megabytes, that would be 10 milliseconds. 10 milliseconds is actually quicker than reading 1 megabyte sequentially from disk, where this is platter. SSD there, 20 times faster so again, reading 1 megabyte sequentially from an SSD is 20 times faster than it is reading it from a platter. And memory is yet 4 times faster. So when you think about low latency, I guess it becomes very, very obvious that it's really, really cool to have as much as you can in memory. But interestingly enough, not accounting for other latency though, I'll get to that later. You can see that actually, if you're not using SSDs, you might be better off reading data from another node than actually hitting a rotating platter. Where obviously this other node doesn't need to go to disk, right? So it defeats the purpose. You want to hit another node that has that same data in memory already. So talking about those NoSQL data stores, there are mainly 4 types that actually you could even refine in 2 types. So there's the key value store. So everybody knows that. That's like your beloved hash map. It just is a key that is used to hashing, like a key uniquely identifying something, and then there is a blob. There's something we have no clue what it is. Could be about anything. Could be like an image, an object graph. Could be an XML document. Those things are really, 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 really fast. But the value is just an opaque thing. So a cache, by the way, would be the perfect example of that, right? So document stores, same thing. I say I have keys. But the values that I store inside my document, the values I store within my store now are documents. Documents of different flavors. Could be an XML document, a JSON document. And the store knows how to understand that document. So using Couchbase, you would store documents in JSON format. and the system of record understands that format and enables you to query it, for instance, which is useful. But unlike RDBMS, each document can be different, right? There is no schemaless, so key 1 could be a customer document, and key 2 could be an invoice. All fine, just a format, so it becomes fixed. And as I said, the cool thing is that all that can then be queried for. Sometimes using MapReduce if need be, because of the distributed nature, generally, again, of those stores. So ones that is probably the most confusing, column family stores. So based on big table paper. So column families, put it there because, like, if you look at Cassandra, they're definitely moving into even like if you interact with the data, well, with them, with the data model, with those words. So a column family would be akin to a table. A row key would be akin to a row primary key within a database. And then I got key value pairs, column names and values, generally also a timestamp in there for conflict resolution. But they can have up to like billions. I think the limit in Cassandra is 2 billion columns per row. And all that is sorted. So one way you could think of this is basically a sorted map that is a row key as its key, and has a value as a sorted map that itself has column keys to column values. And you can even add yet another level of sorted mapping in there with this concept called like super column. Thinking about this model and how to insert data in there so it becomes meaningful and useful to query isn't necessarily easy. It's an exercise. So I put a slide there. So that's Cassandra CQL. So their query language. As you can see, this probably looks familiar, right? So we got graph databases. So when I said, before I move on to them, when I said you could group your NoSQL like in sort of 2 families, the first 3 we just covered, right? So the key value, the document, and the column family one. If you think about it, they're like really cool for those aggregates we talked about. They really like group things in aggregate. Like in PAX, again, obviously the data model and the way you model stuff to put like your state inside those systems. I'll come back later. I'll come back to that later. But that's really one easy way of thinking about them, or at least it is to me. It was easy for you as well. So then we got graph databases. So as the name implies, they're based on graph theory. And so a graph database uses nodes. It has properties and it has edges. And so edges are used to define a relationship between nodes or a node and a property, and edges themselves can have properties, nodes can have properties. So the very stereotypical example that people always use is like Facebook and your friend's graph, right? So everything that is mainly defined through relations. Well, this is when I should say relationships of things. So not relations as we know from relational database. And there is one line that I find becomes blurry for a given product as well. And that's the key value store versus document store. Not necessarily all key value store would consider the value an entirely opaque value. But I don't think any really ever understands the complete value, right? So a document store, again, it understands the language, so say JSON that defines your document, so it can go in there, it can navigate it, do a bunch of things. A key value store doesn't do this, but it can possibly like retrieve information about it can enable you to retrieve information about the value that's in there. So one example is, for instance, searchable. So a bunch of key values become searchable. But instead of sort of, I hate saying dynamic because some, including the product that I work on supports dynamic discovery of things. Only it needs to sort of be preemptive, i.e., you put something in the key value store, we can have your code that you provided us called an attribute extractor look at whatever the payload is, i.e. the value in that case, right? Retrieve information out of it and use that to enrich the data, right? So in case of a search, that enables you to, for instance, keep an index up to date so that I can then easily query my key value store for what can I use as an example? Like all products, and I index the price of things. I want to find all products that are more expensive than $100. I can now query for this. But the data store, well, the key value store itself doesn't understand really the value itself, right? So your thing could totally lie. You could say, all right, that's not a product, that's a customer. Sure, it will blindly trust you. Because it doesn't have any semantic to it anyways, right? It won't build on anything then with that. It's only for stuff that you ask it that will give you the value back. All right. So we said all those NoSQL store are distributed in nature. So what does this all mean? So that's welcome to the distributed world. Bye-bye ACID, or at least as we know it. And I've put Hello Cloud in there because I think that is probably the most, like, the thing that's the easiest to relate to, right? In terms of big computer farms, server farms. So we're in the cloud age. Ding, keyword. This almost sounds like a marketing presentation, don't you think? With that many keywords in it? I think it's very good. It's a technical conference, and it's here. So cloud is about scaling out and not up, right? Again, same thing, bunch of hardware. I add servers I need as I see fit. Servers are generally commodity hardware, even though the definition of commodity hardware is being stretched sometimes, but yeah, it's true. It's not a big Oracle rack. And so I add and I remove nodes as I see fit or as I need, most probably. And that leads me to the situation I talked about before, right? I end up in a situation where the more server I have, the sooner one fail. The sooner one will fail. Sorry. And that's just a fact again, right? It's not a maybe, it's gonna fail. You know, it's like when you don't do backups, you're like, all right, everything goes fine so far. Everything goes fine so far. And then the hard drive fails, bye-bye all my music. And that's how people move to ding, 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 bunch of keywords. Other NoSQL data stores move from this ACID that we know so much to what they call base. So base being basically available, soft state, eventually consistent. Which means that by default, we try to make sure that everything works. A node disappears, all fine. Let's say that we can move on. Nothing is really necessarily blocking. But when stuff goes south, most probably, well, it might not be, the answers I give you might not be entirely right. But look at the bright side, eventually we'll get there and stuff will be consistent again. Right? Who can reason about this, what I just said, and think it makes sense? Like, you guys are smart. The first time I read this, I'm like, what the heck am I supposed to do with this? Ding, keyword, the cap theorem. Who's heard about the cap theorem? All right. So the cap theorem says that, so you got consistency, you got availability, and you got partition. And you can only choose two of them. But in a distributed system, there is one you're not going to get to choose. It's the partition. It's going to be there. It's not always going to be there, but it's going to be there, right? See, previous point, I got many servers. One is going to fail. It's just a matter of time. So now I need to choose. In the face of a partition, I need to choose what I do. I'm either being consistent or I'm being available. So what this means, say I got a distributed system. I'm going to use a very simple example. Think about a sharded database, right? I got 2 servers, and customers are being randomly hashed to a particular server. So when I ask for user 123, I need to go to server A. When I ask for user 5, I need to go to server B. Right? Now I do a get that can either say, all right, here's the value, or there is no value. Right? It's kind of the same with if I choose availability. Right? I can say, all right, server. So I choose the example of 2, so it's kind of it's in the big distributed world. 2 is obviously not a very valid number. But what does it mean, right? I'm not getting an answer. Does that mean, well, I'm getting that user 123 isn't there. So what does that mean? Is the user not there? Is it non-existent? Or is the node that holds that data down? All right. We'll see how this is all, like, what this really means for you in terms of code and thinking afterwards. Or I can detect the partition and say, all right, I know that node A is down, and since I need to access like user 123, and since I can't figure out whether it exists or not, right, since that's the question you're asking me, I will just block. And I will block up until, well, block for an exception, what have you, but basically I'm not available anymore, right? That's what it comes down to. My system doesn't respond anymore. And that's all in the face of a partition. But what is being partitioned? So the obvious example of being partitioned is a network failure. I got my client machine that talks to a bunch of server, and then I'll suddenly can't get to that server anymore because the network's down, right? That's a fairly obvious example of being partitioned. It could be the machine that's down, entirely down, like server A crashed and burned, all gone. It could be that the process on the server failed, or it could just be that I'm getting to too long response times. So I guess some of you are Java developers, and if you're not Java developers, I'm pretty sure you run on the JVM, right? Who's running their software on the JVM here? Just to make sure that everybody's still awake and I'm in the right conference. Cool. So you run in the JVM, and the JVM is this thing called the garbage collector that sometimes does stuff that takes too long. What is too long? Again, it's a definition that you have to define. But basically, this system is not being able to give you an answer given to your SLA, so that's a problem, right? So what's going on? Am I partition? Is the network down? Are the packets going to dev null? Or is the server just in a long GC and I can't get to the data that I need? So in the meantime, I don't know, right? I'm querying the system and I'm not getting the answer I want. Right? So I need to define this partition from my application perspective, right? It's not driven by the system of record itself. It's actually driven by your needs, right? If every query to a system of records needs to happen in, say, I don't know, pick a number, then that's my SLA. That's what it needs to obey. If it blocks for longer than that, I can consider myself partitioned. So an example of that is the way that Terracotta does distribution. I'm going to show you how we let users deal with this partition and stuff. So the clients that you see down there are actually JVMs running your program, whatever your program does. And it's talking to what we call like stripes, TSA stripes. You can consider it as one TSA, but basically these are multiple server nodes that contain your data and are responsible for a bunch of different things, including synchronization and blah, blah, blah. But sorry, let's not talk about this. Let's only care about the partitioning problem. And then something goes south, right? So flames, almost as cool, actually cooler than buzzwords. Network's down, right? So my client here needs to talk to this TSA stripe that holds, again, my customer 123, can't access it, crap, I'm partitioned. Now, the thing is that all the clients hold what we call a first level cache that can be actually pretty big. So that's on the machine itself, right? And so whatever goes south, so if I take the example of, again, the TSA, so every Terracotta server process is running within a JVM. So this guy could be in full GC. And I got this SLA, and I need to get an answer in X time. I can configure now my system to act in different ways. So in case of a partitioning, this partitioning, I define it based on time. I say, when I ask you a question, I expect you to give me an answer, say in 15 milliseconds. If I'm not getting the answer in 15 milliseconds, I need you to take the other route. I need to remain available, whatever that then means. So I can configure on what I want to happen in case of a partitioning. I can say the most obvious and the default thing the default behavior that a terracotta client will have is actually throw an exception. It's saying, crap, I tried to talk to this guy, couldn't, I throw an exception. It's an exception of non-stop exception, I think it's called. And your application needs to handle it. But we have other behaviors. We have the no-op behavior, right? So we expose everything to the Ehcache API, which is a caching, a cache service, as the name implies. That's initially what it was built for. So it's a cache. A cache is sort of a disposable resource. So you could say that it's a no-op. I say I was trying to get customer 123. Well, I can't get a response in 15 milliseconds. Screw it. I consider a cache miss. All right, this guy is not in the cache. So now I need to do something else, right? A cache caches. So I need to go to a system of record or do something else. The same for a write. If I can't do the write in time, I just let the write fall to the floor, kind of akin to the thing being evicted from the cache because of capacity or whatever. It's not in the cache, but my application happily keeps on going. I can read local. So this L1 cache that sits there could have customer 123 there. That could or could not be up to date. No, right? It's in there. We're partitioned. In case an update comes, my client will not be informed of that. So I may be looking at an older version of my customer, but I can return. I know my use case. It's fine. I'm just returning that and happily move on. A write becomes a no-op, saying, all right, in that case, I can read locally, but I can't write locally, right? This would need that I need to introduce a queue again. This queue could grow. I don't know how long the partition is going to take, right? So, and I don't want my client to me. So I don't do that. Then I get local reason exception on write, which is basically a merge of the first and the third option. So for a read, if the data is local, I return it. If it's not, it's considered a miss. But when I write, say I don't use my cache as a cache, but actually as a data store, I can't do a put inside my cache, and then the thing is being dropped to the floor, right? I actually need this data to be in there. I know it will never be capacity evicted because that's turned off or whatever, right? So I'm using this as a data store. I cannot afford missing that data. So you can configure it this way. There is an exception. Again, up to you to decide what to do with this. So yeah, I only focused on puts and gets and those behaviors, but actually not all behaviors, well, not all operations are necessarily equal. They are sort of longer running operations. One obvious example is a search query, right? If I issue a search query to my server, I can't hope for the answer necessarily to come in 15 milliseconds, right? It could be a very complex query on a huge amount of data. I need to be able to handle these specifically. Another example is acquiring a lock, right? When I say, all right, I want to acquire a lock, I don't know whether this lock is being held. I don't know whether I'm the next one in the queue to grab that lock. And I'm fine waiting. It's cool. If you're not fine waiting, we support the equivalent of the try lock that you know from the Java YouTube concurrency stuff. So you can say, all right, try to lock this thing within that time, and if you succeed, return true. If you fail, if you can't acquire the lock in time, then return false. And again, you take a different code path and you do whatever it needs be. So that's nice. Let's go back a little to this eventual consistency. So how eventual is eventual? So quoting here. Changes made to one copy eventually migrates to all. If all update activity stops, after a period of time, all replicas of the database will converge to be logically equivalent. Each copy of the database will contain in a predictable order the same documents. Replicas of each document will contain the same fields. Who understood that? Like, you're all so much brighter than me in this audience. We should switch. Honestly, what am I supposed to do with this? So what you're telling me is that I'm changing data all over the place, and then I stop at some point in the future, totally undefined, like everything will be the same and will be consistent. Awesome. That's going to make my life really easy. Now I can go and code to that. I exactly understood it. At least you guys got it. I'm really happy because I'm like, crap, I'm in trouble. This is like really, really weak. What does it really? Basically, it doesn't guarantee me anything, right? What's up with like all activity stops? I don't know. Oh, it's 5 o'clock. Sorry, guys. Service goes down. We're waiting a bit so that we can have a look and produce this report for business so that they're happy, right? This makes my head spin. So what do we do with this? Well, sometimes actually eventual consistency is good enough. And it has like very cool benefits, right? Avoids the long blocking I/O. We move the problem to the data store, right? If I retake this example of sorry about the coughing all the time. I spend too much time in airports and my voice is really, really bad. So if I retake this example of ACID transactions and an update is pending to another transaction and I'm blocked, obviously the throughput of my application goes down, right? Here we move the problem to the data store. It's eventually consistent. At some point, stuff will converge to a consistent state. That's nice. And eventual consistency, so, right, and this advantage that I just gave, you're benefiting from that, not only in the case of a partition, right? It's, oh, cool, I don't need to wait for the write really to happen necessarily. It just will happen eventually. In case of writing data, when we're thinking about is the last writer wins. What last writer wins means depends mainly on the story you're using and how it approaches the problem. Generally, you would want something that uses a clock value of some kind whenever the message itself was written, and that's what you want to have applied generally, but not necessarily. And so how do we deal with failure in such a case? Because if I retake the example of using in this terracotta example I just showed previously, I was actually totally disconnected from the thing I need to write to. Now I need to do a write. How can I make sure that actually the write is not an issue in the face of a partition? Well, one solution is write to more nodes. And I'll show that later using Cassandra again and how you can play with that. But sometimes the eventual consistency is all you need. So depending on the data you're working with, maybe eventual consistency is good enough in all cases and you don't need to care so much about it. It'll just work. So there's this contest that lets you validate that something is consistency as logical monotonicity. Fuck, I hate those. Mouthful. But probably a bunch of buzzwords again. Very cool. And that certainly applies when all your data is immutable. Right? If you think about a system that never changes state, where the data never changes state in your system, you can apply such thinking. So it's functions you can test for on your data to see that it works is this ACID 2.0, as they call it, making sure that your data is associative and commutative, right? So in other words, we don't really care about reordering happening, and what can I use as an example? I don't know, like incrementing by 1, right? If I'm at 3 and I increment by 1 and then by 1 again, I always get at 4, and now if those two writes get reordered, it's all fine, right? I'm only incrementing by 1. we don't really care which one comes first. Idempotent, i.e. if the same function is applied multiple times, it's always the same result. So this adding by one doesn't qualify. And distributed. Actually, the D is only there to be able to make the acid stuff work. But we're talking about things in distributed systems. So commutative replicated data types. Who has heard about these? These are very interesting, even though they're a bit of confusing as well. They actually prove to have those attributes, those properties, sorry. And so some people actually implemented them. Data structures as set, graphs, and sequences that actually have those properties and that you can use in a distributed system so that you don't really care. You just use them and it will just always work. So if your data fits this paradigm, you can actually use these. But sometimes that's not good enough. So we're still left with an open definition of what it means to be eventually consistent. And two guys at UC Berkeley that also work on Cassandra came up with this probabilistic bounded staleness. Staleness, yes. And this concept, or it's actually, you give it numerical values, tries to answer this question. Well, those two questions, actually. In how long will a write be readable by all? How long does it take? So I do a write, it goes to my distributed system. How long does it take for this write to be visible by all? So say that's the one and single write that I made to this key, there are no further ones coming around. How long does it take so that everybody sees that same value? And the other question is, how many old values are still around? So when I query a data, how many potential other values are around the system, right? So for instance, 100 milliseconds after a write, 99.9% of the readers will see the latest value, right? That's a numerical answer to the first question. Or 85% of reads will return a version that is within the two of the most recent values, right? So when I read data, 85% of the time, I'm actually getting one of the two most recent values, either the latest one or the previous one. Again, that gives me like a real answer on how eventual is in my system. So those properties actually depend on a couple of things. So obviously the network delay, right? That's the first thing in the distributed system, right? I'm doing network I/O. I'm sending stuff off to another system, and it acts it one way or another. This introduces latency. The node processing time. Once the node has received this information that value foo has been moved from bar to baz, right? It needs to process that. It gets this bit of information from the network and needs to process it. That takes time again. And last but not least, delayed replication. So delayed replication is think of batching, right? So if you're replicating over a WAN link, for instance, and you've got like really high mutation rate, there is no way you can set an event for every mutation over a WAN link, right? The latency of the whole, so point one, is not neglectable, it's not reliable. So you batch things. You send stuff in batches, potentially coalescing them, right? So that if 10 writes to a single queue happen, you don't even bother sending the 9 values that were in between. Just send the latest one through the pipe. Now, the problem is the one I just said, right? You need to wait for values to come in. If you do something like that because you want to, right? It doesn't happen magically. This will increase again the time. So these are two quotes from the paper that they produced, which I think is very, very interesting. So if you look at the answers that LinkedIn and Yammer got, in my books, this is pretty amazing. So I shouldn't say that because I'm actually about to say that like competitive products is actually really good. But so because this is using Cassandra clusters, this is really good. I find it like really interesting to get to the really that data. Actually, so we're probably actually looking at implementing the same thing inside Terracotta cluster because right now we can't really give you those answers. Sort of weird ways of checking it. So they got also a website on this where you can actually play with the data and sort of feed a bunch of those variables in, and it actually tells you what your PBS will be. I found this very, very interesting. So that's eventual consistency. But do we really need to choose for that? Always, right? Well, as it turns out, so if we go like, I like to think of the base versus acid not as a one or the other. I like to think as of a slider that you can move around depending on on the use case, right? Thinking about not all the data is equal or not all the data being equal at the same time. I'll give an example in a sec. But as it turns out, like you can also go entirely to the left and just account for it and compensate, right? This infamous example about the ATMs that actually will, in case of a partition, will let you read the raw data without being able to check your balance, thing is one obvious example, right? So they'll let you read the data. If you actually read too much data, well, your bank will actually apply fees on you because you actually went like to a negative balance and you're not supposed to do so. It's all compensated at the business level, right? That's one way of thinking about it. But sometimes as well, it's very context sensitive. So the consistency guarantees that you need might really well depend on the use case you're in accessing the same data. So one example is, say, a booking system, right? So I was searching for a room in the area. So we was using some website. Well, I just query, all right, find me the hotels around Ehcache. But obviously, find me the hotels around Ehcache at this period of time that have available room, right? I don't care about hotels that have no room. I'm looking for a room like now. Well, when I make this query, right, I don't care about like ACID consistency. It's what does it even mean, right? Oh, at the time we committed the transaction, when we got this request, it turns out that all those hotels were actually available. Well, then all those bytes have to be streamed through pipes to my computer, be rendered in my browser, and as it happens, the one I will be looking at is the 10th result on the page, so I need to scroll, and I'm very slow. I'm not a fast reader, so I read the whole thing. Actually, by the time the photons that actually comes out of my monitor that actually prints on my thing tells me that room, that I don't know even which room it is, but says like 2 rooms available at the Holiday Inn here close by. They might be long gone by that time, right? So I don't, what's the semantic of like ACID in that case? Nobody cares. Just give me good enough, like approximative result is way better. And giving me like high throughput so that I can handle many searches for available hotel rooms is way more interesting to my use case. So I just query the data, in a very base way, just give me whatever you have. So if I retake the example of Terracotta, if I got this data available on my node, don't even bother going to the server. If an update is pending, it's going to be arriving to me anyways, right? So so what we do at Terracotta is if you have a value, say for this hotel room, on your local node, and somebody else reserves the hotel room, like the server is going to invalidate this result in your local cache. So from the back, we don't necessarily push it eagerly. There are ways to do that as well, but think of it like as simple as possible. So we just invalidate the thing. We tell this now, hey, get rid of this because the value you have is not up to date anymore, right? So it's within the last, say, 100 milliseconds, this result was actually perfectly valid. So that's good. It can be part of the result set. And now when I actually go out booking my room, This is when I care about when I open the door that there isn't somebody else in the room, right? That's where I care about, making sure that I'm the only one booking the room. And this is when I want to like slide the slider to the opposite direction. When I'm actually in the process of booking this room, this is where I want to be sure that stuff goes right. Again, doesn't necessarily be the case. You can go back to bullet point number 1, right? If you think of Amazon, right? That's the way that Amazon does business. The only thing that they care about is they care about getting your order, right? And yeah, the thing that said that this item was in stock was probably right. And if it's wrong, well, we compensate. But you can search for like, being able to move the slider is actually pretty powerful. So how does that all happen? So again, taking an example from Cassandra CQL. Doesn't that look incredibly SQL-like? I'm selecting like all the users that are in the state of Texas, and I'm using a consistency of 1. So however I set up, I don't want to go into the details on how you set up a Cassandra cluster or a Terracotta cluster in this session. That's not the point. So again, think of it as data. So in this case, my Cassandra cluster, like the data is available on multiple nodes. And some nodes say are like the master, and the other ones are replicas. So the replicas could be slightly out of date, but that's fine. I don't really care. Right, so a write came to node foo, and got it all replicated all over the place, and I'll explain a little bit more about masters and slaves anyways in the next example in the insert. So it's fine. As soon as you find a user, just give me the answer. That's cool. That's good enough for me. That's a consistency of 1. I can raise that and make that a consistency of 2. I fetch 2 things and make sure that I get the right value. Another interesting thing that Cassandra does, when I ask for a consistency of 1, the server will return the result that it has right away, and in the back, it will trigger what's called a read repair. I.e., the value that's served to you, it will try and make sure that this value is correct. Right? It won't like give you an event afterwards saying, oh, by the way, send me those bytes back, didn't meant to send you these. No, that's not that. But it gets its value updated. So if you rewrite the value from the same node, you're actually pretty sure you get a later value validated. On the insert, you see that I use a consistency of any. What could any possibly mean? Any is actually even less than 1. What this means is that, all right, insert this thing, but honestly, I don't care, right? It's an employee anyways. Who would care about his employees, right? Just insert this thing and make sure that eventually it gets somewhere. So in case what this thing hashes to, like all the nodes are down, right, that need to store that data, it can actually decide to write to a random node. And whenever the other nodes come back, it will push this thing to those nodes. It's what they call a hinted handoff. Now, obviously, this only works for writes, right? You can do this with a read. You can say like any, give me any answer, because you don't know, right? It would mean that the data would need to be replicated all over the place. But for a write, you can do this. You say, all right, I don't care at all. Just write this thing. Now, if you would try to read it back, though, you wouldn't be able to get to it, right? That's what it means, because there is no node that actually has that. Another example that's from the Ehcache world. So we create a Terracotta config. A Terracotta config goes inside a cache config that is then being used to create a cache. That's utterly confusing, but that's the way it is. And I set this cache to be eventually consistent. That's the view that I want to have in the data in this cache. And then I realized, whoops, crap. I need to raise the, actually I should have said sorry for the regression, if we go back here. You can, to use strong consistency here, you would say all, right? read from all the nodes. So they correlate. Remember, Cassandra is a column family, so there is a timestamp associated with all things, well, with all columns, so that they can actually merge the thing and you get like the totally up-to-date, the real thing. What is the very latest state? You ask all. That's the consistency you would ask for. So back to Ehcache. So I create this a view on a clustered cache that is, as you see, clustered, is eventually consistent. So it's really, really quick. And now all of a sudden I need to, say, book my room, because I'm using Ehcache as a system of record. I can then use a strongly consistent cache accessor that actually decorates my eventual cache reference that I have. So that's the eventual cache that I passed in, right? So when I do this get, like the second effective line of code, this eventual cache.get potentially returns me the value from the local cache, not making sure that it's the right one. But at some point, I need to be sure that I'm really the one doing things, and say that I use my cache as a system of record, or through some very evil key, I make it so that booking a room is actually akin to a put if absent that succeeds, right? I managed to put this thing in, so that's it. So basically my cache is a finished state machine. I put this thing in, that's the reservation now. And so in order to make sure that this really happens like consistently, I create this strongly consistent cache accessor and do this cache accessor put if absent. A regular put would work as well. A get would then also be like really strongly consistent, i.e. making sure that it returns you the real value from the server. In our world, what this means is that you grab a lock, a read lock to this thing, nobody can mutate it, you read the value, get it back, and you move on. All right, so when having digested, sort of, all of this, revisiting our tiering, we actually moved some concerns now to the middle tier, right? Transactions, even though there are ways to sort of get akin behaviors from non-transactional stores, they're not handled by the system of record anymore. Right? Search, not handled by the system of record. Caching, same thing, right? If I want to be smart, my application server is not going to put like things in like around in memory. So remember those latency figures I gave you? Right? They just are. The database will apply those kind of thinkings at all times. That's probably one of the reasons we use them, right? Again, 30 years, they haven't been picking their nose, right? They tuned the crap out of this thing. And so they apply a bunch of tricks like that. Nobody does that for free for you in your middle tier. So you're all on your own now. Way more thing to handle. So having said all that, cool. So there are all those stores, RDBMSes. What should I use? What shall I do? Well, I would say you should use them all. And when I say you should use them all, I'm not saying, hey, next application you build, make sure it has a RDBMS in there, a document store, a key value store, a column family store, and a graphs store in there. That's not what I'm saying. I think you should use them all. You should go look into, pick one randomly. Say, all right, I want to look into a graph database. I'm going to pick Neo4j. I'm going to like install it on my computer, and I should use it. I think you should understand those things like hands-on. You know, it's like programming, right? I think you should all be polyglots, and the same is true for data persistence as it is for languages, right? And then you can make decisions as based on the context, right? The easier the better. Whatever is easy, that's what I would do. I'm lazy as one can get. That's why I'm a developer. So I do whatever is the least effort. I think it's important to be able to understand that what will be the easiest is really make sure that you understand the requirements that come from the business that ask you for a solution, and then also the other way around. If you go for a certain data store, the constraint that it will impose on the solution. Say business comes to you saying, oh yeah, we don't care about search, whatever, put stuff in a cache, that's good enough, like really sure, well, they really need to be sure, right? The data, they say, whoops, so actually, no, it would be really cool to be able to query the thing, and you pick the data store that doesn't support any search, that's blazing fast. That's true, but no search at all? Well, you'll have to rethink the app, potentially port the data set to another data store, right? So you need to understand the nature of the data that the system will be dealing with. If it's read mostly, just find the thing that will be the best use case, fit the use case the best. So everything's, I'm not sure how we call that. I'm still going to call that Web 2.0. It's probably not up to date, so I won't do the ding buzzword here. But let's say we got this application. It's totally Ajaxified, and what it does is when you click something, it hits the server. The server answers with a JSON stream, and that updates the DOM automatically, and I got a wonderful UI. It's just awesome. So that's my use case. Awesome. I think we should really make sure. And oh, and by the way, the information I display, say, like kind of a publishing information like articles and whatnot, something that actually is a very good fit for a document store, but I don't care. I'm going to store that inside a relational database. So I can apply all my ORM magic, make sure that at least 20,000 transformations, i.e. the request comes in as JSON, gets parsed using, I don't know, whatever's the standard for parsing JSON and RS web services in Java EE. I parse all this. This then gets transformed into a domain model that goes to the database. I load stuff, comes into memory as an object graph, really huge and complex, so that I can transform that again into JSON and send it to the browser. Wow, I applied math skills, but I was not lazy. Might not be the best solution. And if it's a read-write intensive use case, you need to really figure out how availability of the data and how transactions fits in there. These are two common. You need to think about these like really early. The transaction stuff mainly, right? If you go for a NoSQL store and you need to apply some kind of transaction like semantic, you need to define the semantic really well up front and make sure you'll be able to apply it, right? Otherwise, you're dead. That leads me a little bit into data modeling, and that's one big capture. I think I'm going to stop after this slide for probably 30 minutes or something. Let's take a quick break. Let me cover this though. So data modeling. When you model for SQL, right? It's all about normalization, right? We care about refining the data itself to its purest essence or whatever. That's not what SQL tries to do. SQLs try to think in terms of how did I say SQL? That's what I said, right? I mean, NoSQL. That's not what NoSQL tries to do. In a NoSQL store, you'll mainly try to think about how you're going to be querying that data, so you can model it all in a way that enables that querying to happen as good as can get. And yes, that will mean you will be denormalizing. Yes, that will probably mean you also will have duplicates, right? They're not necessarily a bad thing, but if you go down that route, again, thinking about transaction, like isolation that you might want to get, make sure that nobody ever sees like two different customers at the two different states for one same customer at the same time, because that's a problem. Well, you'll have to think of this when you model your data and your queries or views. Anyways, I guess we should take a 30-minute break. So it's 10:47, I guess. Is it? Yes, it's 10:47. So let's get back here at 11:15 and continue, so you guys can grab coffee or hit the restroom or